Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that's easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos and comment below on videos you'd like to see in the future. This is part 3 of a series I have on complex numbers. In part 1, I went over what imaginary and complex numbers are and how to perform basic operations on them. In part 2, I went over how complex numbers are used as quadratic equations, and I'll link both videos in the description if you haven't seen them yet and would like to check them out. In this video, I will explain how to find the angle and radius of a complex number. This is needed when putting complex numbers into polar form, and I'll get into polar form in the next video. First, I'll go over how to find the radius. Here we have the complex number plane, which recall from part 1 is where all complex numbers are found. The point 0 can be called the origin, and this will be our starting point for finding the radius. Let's say the complex number we're trying to find the radius for is 1 plus 2i. The radius is going to be the distance from the origin to the point 1 plus 2i. Since we are measuring distance, the radius will always be a positive number. To find the distance, we're going to need the help of right triangles. According to the Pythagorean theorem, which you may recall if you studied geometry, the distance of the legs of a right triangle squared added together is equal to the hypotenuse of the right triangle squared. We can also solve this equation for the hypotenuse, writing that as equal to the positive square root of the distance of the legs squared added together. The negative square root does not apply here since we are measuring distance. So, let's say for example our two legs are 3 and 4. The hypotenuse is going to equal the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. And so our hypotenuse is 5. Trying a different example, with the two legs equal to 3 and 5, we can see that the hypotenuse is going to equal the square root of 3 squared plus 5 squared, which is just the positive square root of 34, which cannot be simplified. So, how can we use this to find the radius of a complex number? Well, we can create a right triangle here with our radius as a hypotenuse. We can clearly see the distance of the two legs is 1 and 2, which are just the two real numbers in our complex number. Using our formula for finding the hypotenuse, we can see that it equals the square root of 1 squared plus 2 squared, which is just the square root of 5. And so the radius of 1 plus 2i is the square root of 5. Now let's try a different example. Here, as before, the radius is going to be the distance from the origin to the complex number. Creating another right triangle, we can easily see that our two legs are going to be 3 and 2. And to find the hypotenuse, we can take the square root of 2 squared plus 3 squared, which is the square root of 13. And so, the radius of negative 2 minus 3i is going to be the square root of 13. So, for any complex number x plus yi, the radius is just simply going to be the positive square root of x squared and y squared added together. Now that we've gone over finding the radius, we can now go over how to find the angle, which unfortunately is not as simple. The angle of a complex number is the angle from the positive real axis to the radius of the complex number. When finding the angle of a complex number, we need to specify that we'll be working strictly in radians instead of degrees. If you are unfamiliar with radians, it is representing the angles in a circle as 0 to 2 pi, instead of 0 to 360 degrees. And for radians, you do not need to use the degree symbol. Throughout the study of complex numbers, it is important to only work in radians, as it is more mathematically driven, representing angles using the distance of the circumference of the unit circle it covers, since recall, the distance of the circumference of the unit circle is 2 pi. To find the angle of a complex number, we're going to need the help of right triangles again. If you've studied geometry and/or trigonometry, you should be familiar with how to find and represent the angles in a right triangle, and you should be familiar with the functions cosine, sine, and tangent, tangent being defined as the sine of the angle divided by the cosine. Calling our angle theta, which is what the symbol that looks like a zero with a line through it is called, and knowing the definitions of these trigonometric functions, we can represent the angle using the legs and hypotenuse of the right triangle. So, how can this be used to find the angle of a complex number? Well, we can create a right triangle as before, and notice that I'm calling the angle we're trying to find theta. Knowing trigonometric properties, the tangent of theta is going to be equal to the opposite leg divided by the adjacent leg, and we can clearly see that our legs are 2 and 1. And so the tangent of theta is going to be 2 over 1, which is 2. Also, the reason we are using the tangent function instead of the sine or cosine function is because the sine and cosine function use the leg and the hypotenuse, while the tangent function only uses the legs. And since it is really easy to find the legs of a complex number, it is more convenient to use the tangent function. We can solve this for theta using the arctangent function, which is just the inverse tangent, which, sticking strictly to radians, is approximately equal to 1.10715. If you try evaluating this on a calculator, it is very important to make sure your calculator is set to radians, otherwise you'll get an answer in terms of degrees. And so, the angle, also called the argument of 1 plus 2i, is approximately 1.10715. So let's try this for another example, 2 plus 2i. You find that the tangent of theta is going to be 2 divided by 2, which is 1. Solving this for theta, you get the arctangent of 1, which in radians is equal to exactly pi over 4. In degrees, pi over 4 would be 45 degrees, and it is easy to see from the graph that the angle is 45 degrees. Learning to work in radians is a very useful skill though, and I would recommend practicing it. Here we see that the angle or argument of 2 plus 2i is pi over 4. The complex number plane is split into 4 quadrants. We've shown examples of finding the angle in the first quadrant, but finding the angles in the other quadrants uses a method a little different. For a complex number in quadrant 1, represented x plus yi, where x and y are both real and positive, the angle is going to be equal to the arctangent of y over x, as we've seen from our previous examples. Now let's try an example in the second quadrant, finding the angle or argument of -3 plus 2i. Here our angle is once again going to be from the positive real axis to the radius of the complex number. What we'll do is form another right triangle where we have an angle x. We'll call the angle of the complex number we're trying to solve for angle theta. Using the methods from before, we can see that our angle x is going to be the arctangent of 2 over 3. So how can we use this information to solve for theta? Well, recall that for radians, the angle of the top half of the unit circle is going to be exactly pi. And seeing that x plus theta is going to be this value, we can write that theta plus x is equal to pi. And recall that we already showed that x is equal to the arctangent of 2 over 3. Solving for theta, we see that the angle or argument of -3 plus 2i is equal to pi minus the arctangent of 2 over 3, which is approximately equal to 2.55359. And so we see that for quadrant 2, if our complex number is -x plus yi, where once again x and y are both positive real numbers, the angle or argument is going to equal pi minus the arctangent of y over x. For quadrant 3 and 4, it gets a little more interesting, however. We already said that for radians, instead of traditionally going from 0 to 360 degrees, we are going from 0 to 2 pi. But when we're solving for the angle or argument of a complex number, we're instead going to go from -pi to pi. Finding a negative angle might seem a bit odd, but it can make sense if you think about the fact that positive angles go counterclockwise, and so a negative angle goes clockwise. And going the angle -pi clockwise using negative angles gets you to the same point as positive pi would get. And so we're going to be solving for angles specifically larger than -pi but never equal to it, and smaller than pi and possibly equal to it. If you're wondering why we're using negative angles at all, think about the fact that the definition of the angle or argument of a complex number is the angle from the positive real axis to the radius of the complex number. And for quadrants 3 and 4, going clockwise will get you there in a shorter distance than if you were to try going there anti-clockwise. And so it is to see that quadrant 3 is just going to be the negative version of quadrant 2, and quadrant 4 is just going to be the negative version of quadrant 1. And we've already figured out what the angles for quadrant 1 and 2 are. And so we know the angles for quadrant 3 and 4 by just writing the negative version. And for quadrant 3, we see that the negative version of pi minus the arctangent of y over x is just going to be the arctangent of y over x minus pi. And so we now have a complete map of how to find the angles or arguments of all complex numbers in the complex number plane in radians. Now let's try using all of this knowledge to find both the radius and angle of a given complex number. Let's start with something super simple, just 3. Recall from part 1 that every number is technically a complex number, even if it doesn't use the imaginary constant. Here the distance from 0 to the number is going to be 3, and so the radius is 3, and the angle is easily shown to be 0. Pretty simple, right? Now let's try another complex number, 2i. Here you can easily see that the distance from 0 to 2i is 2, and so the radius is 2, and the angle is just going to be the radian equivalent of a right angle, so pi over 2. Now let's try a more complicated example. Let's say our complex number is 5 minus 3i. Using the Pythagorean theorem and the methods from before, we know that our radius is going to be the positive square root of 5 squared plus -3 squared, which is equal to the positive square root of 61, which cannot be simplified. To find the angle, we notice that our complex number is in the fourth quadrant, which means that the angle is going to equal negative arctangent of 3 over 5, which is going to equal approximately -0.54042. And there we have it. We've shown how to find the angle and radius of any complex number. Here I'll also like to note that the operation of finding the angle or argument of a complex number is often generalized using something called the atan2 function. For any complex number x plus yi, the angle or argument is going to equal atan2 of y over x. If you're curious what this operation looks like, I'd recommend researching it. I now have reached the end of this video. Thanks for watching. Please subscribe to my channel and keep an eye out for future videos. In the next part of the series, I'm going to go over how all this information about the radius and angle of a complex number can actually come into use. Please leave a like and leave a comment on what you thought. Farewell for now.